In this video, we are going to talk about application quality of experience dynamic SLA policy, which is part of Juniper CSO SDWAN solution. We are going to observe three metrics: packet loss, RTT, round trip time, and jitter, and see how system reacts when these metrics are violated. So let's first set the stage for the experiment we are going to do with the live traffic. So we are going to use a spoke device, which is NFX250, a hub device, which is SRX 4200. These two devices are connected via two different interfaces and two different networks. These networks are of no importance apart that we ask that they carry IP traffic. So we have CSO, which is Control Service Orchestrator, that is going to orchestrate these elements. First thing that CSO is going to do is going to instantiate a virtual machine of on our spokes, so the traffic can move from one vSRX to the hub, which is also an SRX device. For this solution, we require at this phase that we have two SRX devices on each end. So clients and servers will communicate through tunnels. These tunnels can be either GRE tunnels only if these are secure networks, for example, private MPLS L3VPN networks, or if this is a public infrastructure like internet, then we are using IPsec GRE tunnels. So on all these paths that exist between spoke and hubs, spokes will be sending active probes. Active probes serve to determine path SLA metrics like round trip time, jitters, and loss. So on all paths between spokes and hubs, active probes will be sent from the spoke device. Also, we have something called passive probes. Passive probes are sent only along the application traffic path and also measure SLAs and violations. So if the traffic takes this path, then over that path we will have passive probes as long as active probes, but active probes are sent on all paths. And also what is important, the best path for an application is determined based on active probe results. There's a lot of theory behind this, but let's say that in AppQoE Juniper implemented solutions, spokes are the ones that determine which path is the best path for particular application traffic. Based on these probes, controller is not involved anymore, and this is what gives this solution scalability, because each spoke will determine the best path and switching will happen locally on the spoke device. So CSO is not involved in determining which path is the best. Spoke is doing that job now. This is in AppQoE implementing solution. Also, on these two paths, we'll introduce impairments so that we can violate those three metrics. And we say which metrics, so RTT, packet loss, and jitter. So let's look now at our setup from the CSO perspective. So we have several devices here. We have two hubs, we have three spokes. One of the spokes that we are going to observe is NFX17. We have tunnels that are established between the spoke device and the hubs. This is a multi-home solution that is used in active standby mode. So we will be concentrating only on the one spoke and one hub at a time. Traffic that we will be using for this scenario is HTTP video traffic. And metrics that we will be violating are metrics that we can configure in our SLA profiles. So these are packet loss, RTT, and jitter. Also, let me one more time stress that this solution is an AppQoE solution. So for that, I'll quickly change to global view. As I want to show you actually our tenants, and particular tenants that I'm going to use is this one. So when we say that this is AppQoE solution, we means that SD-WAN mode here is real-time optimized. So having said all that, let's look at screens where we will be observing what's happening. So for this scenario, we are going to use a breaking point, which will generate HTTP video traffic. So let us start this traffic. And what I want to show you is that this traffic not only being realistic, that here we are talking about number of sessions. So this is not a one session, it's a number of sessions that are established between client and the server. So let's see what kind of sessions do we have. So we see that sessions are being established and also they're being torn down. So we are for SD-WAN solution, when we test SD-WAN solution, it's very important that we work with the real traffic, at realistic traffic as much as possible. We have our impairment machine, those two lightning things on my previous presentation. This is the impairment machine. This machine is gonna introduce delay. They are going to introduce packet loss and jitter in those links. And obviously we are going to observe those two links 2 and 3. These are our one links that we could have seen on the presentation. This is a vSRX that is instantiated on our spoke device NFX17. This is NFX250. We have a vSRX entity virtual machine that is instantiated with one links. So traffic will be switching between these two links. And also we are observing HTTP video traffic that is currently flowing. Around 100 meg of traffic we are sending. So these are passive probes. We currently see that all metrics are normal. And then we also have active probes. So we have four tunnels between two hub devices, one spoke and two hub devices. And we will observe also what's happening with active probes and passive probes. So having said all that, now let's move and start executing 3 tests. That we are going to observe is packet loss, and we'll see what happens when packet loss metric is violated. So again, we have our HTTP video traffic that is being sent with the rate of around 100 meg per second. This is number of TCP sessions, not one session. The traffic currently is using egressing via Gigabit Ethernet 003 and ingressing through Gigabit Ethernet 004, which is our LAN interface. We have only one links, that's 002 and 003. So when violation of packet loss metric happens, we expect the traffic switch from 003 to 002. Again, our passive probes are currently saying that path is clear, there is no packet loss on this path, and active probes are measuring or fall for tunnels that we have to 2 hubs. So active probes are also saying that all 4 paths are clear from packet loss. So let's start and introduce the loss through our impairment machine that is in the path of this traffic. But before that, let me not forget just to show you that current packet loss that we can tolerate is up to 30%. This is in our SLA profile, which is attached to the SD-WAN policy on the spoke device, which is NFX17 in our case. And also, if we look monitoring link switch events under the monitoring tab, we can see that last switchover happened around 3:43. Now it's 4 o'clock. So we expect to see another entry here with time around 4 o'clock when link switch occurs. So let me introduce this loss of, I will be using 40%, a little bit more than 30% so that we can amplify this case. So we can see that immediately TCP is backing off. We see that measurement on the passive probe start to increase. The system has reacted and moved the traffic from interface gigabit Ethernet 003 to gigabit Ethernet 002. Passive probes are now again clear. There is no loss here. Let's see what active probes are saying. Active probes are telling us that two tunnels have currently loss of up or above 40%, which is expected actually. So this all looks good. The last thing that we need to check is obviously the monitoring page and see whether we have caught on our link switch whether this event has been recorded. And sure enough, at 4 o'clock, we see that we have a link switch event. And we see that there is an error on the loss, which is 40%, 46% measured. This is statistical measuring, averaging. And target was 30%. So with these results, we are happy. The system has reacted as expected and moved traffic from a link that experienced from the, let's not say a link, from the path that experienced the problem, in this case packet loss, to the path that is clear of packet loss. This metric that we are going to observe is round trip time. So let's see what happens when this metric is violated. Let's get back to our screens with traffic and different statistics. So 100 meg of HTTP video traffic is being sent. Many TCP sessions. This is not one TCP session. Traffic is currently leaving through interface 002 and ingressing through 004. 004 is not of interest. This is our LAN interface. 002 and 003 are our WAN interface. So when the delay happens, we should expect the traffic moves from 002 to 003. Our current passive probes are telling us that delay round trip time is below 1 millisecond. Active probes on all four paths to destination are also confirming they're clear of the delay, so they're all below 1 millisecond. So before we introduce the delay on our impairment machine, which is in direct path of the traffic, let's first see what kind of SLA profile we have for this type. For HTTP video traffic, we have an SLA profile that can tolerate up to 50 milliseconds of the delay. So we need to violate this number for application to move from one link to another link. So this SLA profile is attached to this SDWAN policy, and this is our spoke device. On this spoke device, the link switchover mechanism will happen. So let's see SDWAN events page with link switch events. So the last one happened at 4:39. Now it's 4:52. Around 4:52, we should see another record here. Okay. So traffic is currently using 002. Let me just introduce a delay of 85, for example, 85 milliseconds. We say we can tolerate 50 milliseconds, so let's see what happens. Okay, something we had a little bit of disturbance. RTT here is saying that it's 85 milliseconds, which is good. Traffic is still on 002. We want this value to clear to go below 1 milliseconds. Okay, it just went to 1. And what happened, we see the traffic moved from 002 to 003. That's good. So let's go back to our SLA monitoring page. Let me refresh. Let's see if we have caught this event. Sure enough, around 4:53, we see that link switch happened, and we see the reason. Because RTT metric is in error, around 85 milliseconds, and target was 50 milliseconds. Other two metrics are okay, loss and jitter. So link switchover occurred as expected, and this concludes this test for RTT. The last metric that we're going to exercise will be jitter or variation in the delay. So let's see what happens when jitter is violated. I must say that it's not very easy to introduce jitter in the system. So again, we have our HTTP video traffic that is being sent and currently using link number 2. We have two WAN links. One is 2, the other is 3. The 4 is the LAN interface for the English traffic. We are not interested in that one. So we expect that from 2 traffic moves, HTTP video traffic moves to link number 3. Currently, jitter seems to be normal. These are passive probes. Actually, sorry, these are active probes. So jitter seems to be normal on the active probes. Passive probes are here. And passive probes follow, as we said, the path of the traffic, while active probes are looking for all available paths to the destination and measure basically all these metrics between spoke and the hub, while passive probe are only following the real traffic path. So jitter seems relatively normal, which is good. Traffic is using 002. Before we do that, let's quickly revisit what we have for the jitter. We are in our SLA profile, we are tolerating up to 5 milliseconds of jitter with delay of 50 milliseconds. That's good. So we have this profile is attached to the SD-WAN policy, and SD-WAN policy is applied to our spoke device NFX17. On the link switch event page, we see that last link switch over happened at 5:54. Now it's 5:58. So around this time, we should see another event being recorded if we are successful to introduce jitter. So let's try and do that. For this, I'm going to use a normal distribution, not to say that normal distribution has anything to do with the delay or traffic patterns or anything like that. So normal distribution here just serves to give us variation on the delay. So a little bit of delay of 10 milliseconds and 10 milliseconds of some kind of a jitter. So see what happens. We want actually the TCP session absorbs this jitter. Okay, we don't want loss. So that's why I'm saying it's not very easy to introduce this. So let's see now what happens. I don't want to see a huge interruption here. Okay, this is good. We seems not to have a loss here. The traffic is still on 002. Jitter has increased. Look at this, jitter has increased. So let's see if traffic is gonna move from 2 to 3. Okay, it seems traffic indeed has moved from 2 to 3. Jitter has gone down. That's good. We have two paths with the jitter, with increased jitter now. On that is what active probing is telling us. Passive probing is okay. Traffic's moved, looks good. Let's revisit our switch link page. And indeed, around 5:59, it's 6 o'clock, around 59, we had actually another event, and it says the jitter has been violated. Look at this. Jitter error 8 milliseconds, target 5 milliseconds. So yes, this seems okay. Uh, the system has reacted as it should. Traffic has switched from 2 to 3. Passive probing now good. So we are happy, and this concludes the last of the metrics that we have exercised.